Okay, we have seen an example of a broken stream cipher, namely RC4. Let's see another badly broken stream cipher, A51. So this was developed in 1987 and became a GSM standard in Europe and USA. A deliberately vacant version, A52, was developed in 1987 for certain export regions. This is because, since cryptography also seen as a weapon, you cannot, distribute to other countries. So if you export it, there has to be some rules. So at the time, the rule was to provide 40-bit security. So the weakened version has 40-bit security so that you can easily perform brute force attacks, okay? Initially kept secrets, reverse engineered in 1999. Of course, you cannot keep this secret if you put the algorithm in every mobile phone, right? Somebody will reverse engineer it. So a GSM transmission is organized as a sequence of bursts. In a typical channel and in one direction, one burst is sent every 4.615 milliseconds and contains 114 bits available for information. Okay. A51 is used to produce for each burst a 114-bit sequence of key stream, which is XORed with the 114-bit plain text prior to modulation. A51 is initialized by a 64-bit key and a publicly known 22-bit frame. Yes, A51 is replaced with A53, which is actually Kasumi block cipher after 3G, but A51 is still used. And actually, you can see that in rural areas or, in places where the base station is old or, and the person you are calling has a very old mobile phone, you have to use A51. But Android is trying to produce a new version of Android where you will be able to block any A51 communication. Hopefully, it will be available sometime. Currently, they are working on this. But nowadays, we don't know which algorithm we are using, right? So, for instance, if you call me right now, you don't know if we'll be using A53, A51, or maybe we will be talking as plain text. Actually, GSM operator might choose this option too, okay? At that point, everybody can listen, of course. A53 supports 384-bit frames when operating in GPRS and edge mode, so this is why you get, better internet speed due to 4G, 5G, and so on. Okay, so the technology changes. So let's look at the picture. It uses 3 LFSRs. Their sizes are 19 bits, 22, and 23. If you sum all of them, it sums to 64. And this is also the size of your secret key, okay? Key stream generation, you start as follows. Your first step is all 3 registers are set to 0. This means that you fill these bits as zeros, okay? All of them. For 64 cycles, key bits are fed to the LFSRs, okay? So you keep feeding them from here, 64 cycles. For 22 additional cycles, a 22-bit frame number is fed to the LFSRs. Okay, so currently you are not producing anything. You keep feeding input, okay? 100 additional clocks with majority function is performed to obtain the initial state. So this means as follows. So we run the LFSRs for 64 cycles, 22 cycles without providing any output. Then without feeding anything, we run them 100 times. But this time it says that we have to look for the majority function. And majority function says this. As you can see, there are red arrows here. So for this 100 cycles, you look at these bits, okay, and check the majority. For instance, if all of them are 1, the majority is 1. If all of them are 0, the majority is 0. But if 2 of them is 0 and 1 of them is 1, then the majority is 0 and belongs to these 2 LFSRs. So in those cycles, you only run these 2 LFSRs, okay? Since everything shifted 1 bit, in the next cycle, these bits will be different. So then again, you check the majority and so on. This way, things will be more complicated because which LFSR you clock depends on the majority function, these values, okay? So let's recall the all steps. Initially, you set them to 0. For 24 cycles, you feed the secret key bits. For 22 cycles, you feed the frame number. Then you run all of the LFSR for 100 additional clocks, with this time keeping mind in the measure-to function. After that, there will be zeros and ones here. So that will be your initial state. From this point on, you will be generating key stream. So 228 clocks are performed to produce 220 bits of key stream, which is XORed with the plain text. Okay. So when you produce the key stream, you still have to consider the measure-to function. Okay. It is omitted only at the beginning here. So let's talk about brute force attack. So it is easy to guess a part of the GSM communication, right? You always capture the ciphertext, and it is easier to guess some of the plain text. So it is easy to capture, I mentioned this. It is easy to capture ciphertext since the communication is wireless and one can stay close to the target or to the base GSM station and capture the ciphertext. So we can always capture some part of the key stream by XORing the plain text and the ciphertext, and then perform exhaustive search on the key to check if it produces the same key stream. So all you need to do, you capture the key stream here. You feed the key to here and check if it also produces the same key stream, right? Then you have to perform a brute force attack for every possible key, which is 2 to the 64. And, we can, of course, the slide is old with new GPUs. I would say that this is 2 to the 36 or 7, okay? We can perform many encryptions using a single GPU. So with 32 GPUs, an exhaustive search of 2 to the 64 currently will take a few months. If you have very nice GPUs or more GPUs, you can do it in days. But the thing is that if you want to listen to many communication, you cannot spend days for all of them, right? The question is, can I do it faster? And the answer is yes. So we cannot spend a year for every exhaustive search. We can do the search once and store the results. Such a search would require 2 to the 64 plus 22, because if you want to do the search first and then use it, you cannot know which frame they are using. But recall that the initial state is determined also by the frame. So you can do this brute force for every frame and every secret key, but this increases the number of encryptions to 2 to the 86, which is hard. So instead of performing exhaustive search on the key and the frame, we can do it on the initial state, which can take at most 2 to the 64 different values. And here we assume that we have a way to go back from initial state to key and the frame, but it is not important. So let me explain what I'm trying to say. So a brute force attack can start like this, I can set all of these registers to 0. I can randomly choose the secret key starting from all zeros, then choose the frame as 0, run the algorithm 100 more clocks and obtain the initial state, then produce the key stream and check, right? This would be your brute force attack. But actually, I can start the brute force attack here, because if I go back, without knowing the key and the frame and so on, after all of these steps, we will have the initial state, right? And the initial state produces the key stream. And since there are 64 bits here, I can check every initial state. I can perform the brute force on the initial states to see if it produces the key stream, okay? Afterwards, actually, I don't need to capture the secret key anyway, right? Because if I know the initial state, then I can produce the key stream and then decrypt the whole communication. That is the whole idea. Okay. So I'm saying that there can be at most 2 to the 64 different initial states, and actually, due to the design of the cipher, we cannot observe all of the initial states. It is even as small as 2 to the 61.16, but it is not important anyway. So assume that I want to perform a brute force for a plain text or for any initial state. I can perform the brute force and store the key stream, right, in the memory. But this means that I have to store at least this many key streams. And this is actually a huge amount of thousands of petabytes, which we don't have, okay? So we can reduce the memory cost by using rainbow tables. This is time memory trade-off attacks. So for instance, in 2010, in a master's thesis at NTNU, people used a few GPUs to generate around 2 terabytes of rainbow tables, And once you are given a 114 bits of the non-plain text, these tables can decrypt a GSM conversation with a probability larger than 19%. Okay? So if you have more GPUs, you can perform more operations. You can also increase this size because nowadays we can buy 8 terabytes of hard drives or 16. So you can easily make this 99% because, compared to 2010, our GPUs are a lot faster and we have better devices, okay? So today we can create similar rainbow tables that would decrypt the conversation with probability larger than 99%. And, this means that if you have a nice hard drive, like for instance, 4 terabytes or 8 terabytes, you can produce these tables, put it in the hard drive, put an antenna to it, put an ARM processor, put that small device in your backpack, and while you are walking on the street, you can listen to every 2G communication in real time. You can decrypt them at real time.